So from yesterday, we're going to continue with the base running example. This time, we're going to look at analyzing paired data using simulation. So recall from last time, we discussed the data from the base running study to investigate whether, on average, runtimes tend to differ between the two base running strategies, narrow angle versus wide angle. So from last time, I just already typed this in. You may want to pause and write it down. Explain why we should treat the data as paired data. Well, because each pair of narrow angle runtime and wide angle runtime comes from the same runner and reflects that runner's skill. So it's from the same runner and it reflects the runner's skill level. So if you had me, let's say, run against a Cal Poly athlete, let's say a track athlete, they would be done and I would still be, well, I'd be out of the blocks, but I'd be really far behind. So it's better instead to compare myself. I'll run it, take a break, run one angle, and then whatever angle I was assigned, and then take a little bit longer of a break. I am in over 50, and then run it again with the other angle. Whichever one I was randomly assigned to first, run that one, and then run the next one the second time. Describe the parameter of interest, so B, and assign a symbol to it. Remember, when we're talking about run times. So hopefully you're thinking, okay, run times, we're looking at seconds. In my case, maybe minutes, but let's go with seconds. Just joking. So the parameter is going to be mu. And remember, we used N and W for narrow and wide. So I'm going to do N minus W. And that is going to be in general, or in the long term, but I'll do with in general, on average, how much longer the narrow angle takes compared to wide. Because remember here, I'm doing N minus W, so that's narrow minus wide, just to remind ourselves. So if the narrow takes longer, it's going to be a positive result. If the narrow takes less time, it would be a negative result when we look at those differences for each runner. So now I'd like you to pause the video for a second and write the null and alternate hypothesis in words and in symbols to investigate whether on average runtimes tend to differ between the two base running strategies. We've done this a lot. This is good practice. Pause and then check your answer. So I have my null and alternate hypothesis written. H sub 0 for my null. Nothing special is happening. So my difference is 0. Looking here. On average, the narrow angle takes the same time as the wide angle. Or you could say that on average, there's no difference between the two strategies. There's lots of different ways you can say it. What you want to do is be consistent between here and here. So if I said for the null that there's no difference between the two strategies, for the null hypothesis, for the alternate hypothesis, I want to say there is a difference between the two strategies, or depending on what sign I'm using here. Hopefully at this point, when you saw the word differ, you thought, ooh, it's not greater than, it's not less than, it's different from. It's going to be different. We don't know which one is better or worse. We weren't looking to investigate that. We were looking to just investigate whether they differ. So I have my H sub A, mu N minus W is not equal to 0. On average, the narrow angle takes a different amount of time than the wide angle. So to look at the graphical and numerical summaries of the data, there's actually an applet called matched pairs, and we're going to go to it in just a moment. So under the sample window, we want to check whenever you open and you think that there should be data preloaded, you want to look and make sure it's the correct data that's already loaded. So remember we talked about yesterday that the original study had 22. We only looked at 10 yesterday because it would have taken quite a bit of time to do the differences for 22 runners. If you want to analyze data from a different study, remember you need to clear the data that's currently in the sample data window and then paste in the data you want to use. Then click Use Data. So I just paused the video for a second, obviously, and went into my canvas. Now my canvas is obviously going to look different than yours, but I'm going to go into the web applets Just want to show everyone where they are. You notice I have the same issue. I have to click on it again here. And I want to look specifically at matched pairs. So it's under statistical inference, and I'm going to click matched pairs there. And let's see. Oh, I can see in the paired data here on the left-hand side, lower down, the ID number for the counts, and then narrow and wide. So when I look at it, it's like, well, what does this mean exactly? They're showing the outcomes up here in the red and the blue, and it's showing the narrow and the wide, and they're paired. So the person who did this first one, let's see if I can, oh, I can't write on this, sorry. Let's see, oh, I can use this. Okay, this person is paired with this. Okay, the blue, wide angle, narrow angle. So let's see, 6.2 seconds and more than 6.2 seconds. So the narrow took longer than the wide for this person, so you can see them individually. This would be very challenging to do by hand, so luckily we have this applet. But what we're interested in is looking at these differences, and you actually have this in your notes if you look under on the next page of the notes. This I copied and pasted, actually used something called Snippet, and took a picture of this and included it. So the mean of these differences is 0.075. The standard deviation is calculated for you as being 0.088. Hopefully I'm not giving you whiplash. So back to the notes. So we notice, so I just wanted to show you where they came from. We're going to go back to that in just a moment. But here, we looked at the applet, and this is what I used, and it's a tool called Snippet, and it's pretty neat. I literally you're able to just cut a piece out and paste it. So this reported the mean and the standard deviation. A screenshot is below. Based on the dot plot, does it appear that on average run times tend to be higher on a particular strategy, narrow versus wide, and how are you deciding? So think about that for a second. Hopefully you said narrow, all right? Because remember, we're looking at mu n minus w. So in other words, narrow minus wide, like we talked about last time. So these numbers are all positive. So obviously 10 minus 5 is, well, let's do 10 minus 6 is 4. So 10 in this case would be the narrow minus 4 the wide. That would give us 6. So narrow is taking longer. You obviously have to write that down. I just wanted to jot that if you're struggling with it. So that's how I'm deciding. I can see it right here on the chart. So yes, for most, the difference is greater than 0, as we see looking at this difference at this dot plot. And remember, we're doing narrow versus minus wide. On average, so looking, remember, average or mean, it's greater than 0. So on average, the 22 runners ran slower with the, why did I write wide? I should have written, excuse me, narrow. Now, did all runners have a higher run time with narrow than wide? And how are you deciding? Think about it. What would we expect to see if all runners have a higher run time with narrow than wide? Well, hopefully you think, I would not have anything down here. There wouldn't be any. There are a handful of runners for the difference is less than 0, meaning the wide run time was higher, but on average, the narrow run time was higher. So no, a handful of the runners, let's see, it looks like I can count 1, 2, 3, 4, 5. So there are 5 of them. The difference was less than 0, meaning that the wide run time was higher. So they didn't all, but most of them are over here. Record the sample size, sample mean, and standard deviation for the differences narrow minus wide. So we want to do this with good notation so that we're comfortable and we're remembering how to do it. Take a moment, pause the video, do it yourself, and then check your answer. Just a few notes about this. You notice that I'm using N for sample size. That is an N. N. And how about, well, that was spastic. N, I already written N once, so N minus W subscript is 22. I'm using X bar here. X bar, remember, we're not, mu is what's happening with the population, what's happening long run. X bar is our sample statistic. We also want to label that N minus subscript N minus W. And once again, I'm just getting those numbers right up here. Something I also want to point out, we're using S. Remember, that's the sample standard deviation. Okay, so that's the sample standard deviation. So that is always denoted by S. So N minus W is 0.088. So the key question, once again, we come back to that key question again and again. Hopefully this is really starting to sink in. How surprising is it to get the runtime to be as different comparing narrow to wide as, well, what are we looking at? Hopefully you thought, oh, the sample statistic, 0.075, or even more on average by random chance alone. We can find out by calculating a p-value. Now, it's much easier than, can you imagine trying to do that when we looked at it yesterday by hand, doing it 1,000 times to get a decent number in our null distribution? It would take forever. So to find a simulation-based p-value using the applet that quantifies the strength of evidence, because remember when we're looking at the p-value, we're looking at how strong, how unusual is our observation from our statistic, from our study. So to evidence that the data provide against the null and for the alternate. Remember, we can never find evidence for the null, right? We can find evidence for the alternate and against the null, but never for the null. So let's go back. It says, go back to the matched pairs applet. We're going to click the randomize box, click it one time, and then we're going to describe what it did. So I'm once again going to pause and pop over. And back to the applet. I highly suggest, if you can, after you watch this, go through this yourself to make sure you're really comfortable. I'm going to click, it told me to click on randomize. So I'm clicking on randomize. And remember, we want to come up with a null distribution. What would happen by just random chance? All right. So remember, before we did it, we flipped the coin, and if it came out heads, we swapped the signs of the differences, and if it came up tails, we did not. So let's do it one time and see what's happening. So I'm going to click randomize, and it's going to do it for each one. And it's showing you what it comes up with, heads or tails. All right, so you see heads, and we we switched the difference. And when it came up tails down here, we did not. So you can see where it was swapped and here, and where it was not, it was just left alone. All right, that ended up being negative 0.04 is what that calculated. Is one time good? No. Let's do it another time. So should the same sort, so that's showing you the number of samples is just one right now. Can I do it again? Sure. I can click randomize. It's going to do it again. Do I expect it to come out exactly the average difference at negative 0.04? It could, but it's unlikely, and it did not. The blue on these tables is always what happened with your last repetition. So this time, oh look, there's a lot that didn't switch this time. All right, so we're looking at this, and it does all 22. Let me do it one more time. Just hopefully you can see this. Okay, I know I'm a dweeb, I'll be honest, but I think this is kind of cool. So it does this. Now I have a total of 3. But what do we want in general? Oh, and this one came out differently also. Do we expect that? Yeah. I mean, each time, remember, this is what's happening by random chance. But we want the total to be 1,000. So how many should we put in total? Oh, how many more should we put in, I should say? Well, I'm going to change this to 997 because we already have 3. And I'm going to get rid of animate because it'll just go crazy. So I'm going to click randomize. And out it comes. Okay. So there is my null distribution. So before we go any further, just look, there are 3 different graphs. We're going to come back and talk about those in just a moment. This, once again, that blue line, if you're wondering what that is as we move along, as you've been doing it, hopefully you've noticed that that is just the last repetition. That's number 1000, that what happened, and it ended up being, looks like 0.02. So we're going to go back to the notes for a moment, and then we'll come back to this. So back at the notes, describe what the applet is doing and why it's doing it. Is it similar to the tactile simulation we did in day 24? Actually, it is. Yes, it's very similar. In fact, it is what we did. For each repetition, so each time we flipped the coin 22 times and decided for each person if we're going to switch the sign or not, for each repetition, the applet tosses a coin for each runner and swaps narrow and wide the run times if it's heads, and keeps it the same if tails. Now, before we know how we just talked about switching signs, in this case, it actually does the switching for us. It then calculates the average difference. It plots this, and it repeats the process again. Once you hit the button again, which is the randomize button. So it's doing exactly what we were talking about before. When we either switch or not switch, it's doing the exact same thing that we did, except that it's able to do it very quickly and does the calculations for us, which is very nice. Now, we noticed before that it has 3 graphs on the right side panel: swapped outcomes, simulated difference, and average differences. So let's go back and take a look at those really quickly, and then we will record some information here. Actually, before I move on, I'm just going to talk through this. I did not record the values. I apologize. Here, I suggest working on this yourself. Run through it, make sure you understand it. But when we look at the simulated differences, and we'll go back and look at those in a minute, what was the mean reported? Do we expect the mean of the simulated differences is one possible value? So the average difference in runtimes could have been if on average both strategies were equally good. Is the value less or more or less extreme than that observed average difference in the actual study and reported the 0.075? And how are you deciding? Well, you would decide by looking at the graph, because remember, we're looking for differences more extreme than 0.075. So as we randomized, remember we got them before, and I think our first number was like negative 0.04. In fact, I do remember. It was negative 0.04, and then I think our next time was negative 0.02. Remember how we showed up? And the last one, I don't remember what the value was. But are these as extreme as 0.075? Which is closer to 0? Well, if you're struggling, let's say that you're like, well, but but these are negative. Doesn't matter because remember we're thinking about how far we are from 0. Okay, so 0's here and 0.075 is way out there, right? And this would be, let's say, 0.5. 0.02 is going to, negative 0.02 is going to be pretty close to 0, as is in negative 0.04. So these are actually closer. These are not as extreme as, oops, I lost a 0 there, 0.075. All right, so they are not. So are the values that we found more or less extreme? Well, there's less extreme because they're closer to 0 than 0.075. All right, so let's go back now. Are the values as you reported the same each time? Remember we said, no, are they going to be the same as we were doing, as I was clicking before? They're not the same. They're most likely different than each other. Because remember, we're doing it, well, let me slightly. Okay. Remember, I'm flipping a coin and I'm deciding so each rep is flipping the coin 22 times, once for each runner, and deciding whether to swap their scores. Could I 2 times in a row come up with the exact same mean of the simulated differences? Certainly. Is it likely? I mean, it could happen. But most likely it's different. And that's what we found as we went through. Over time, though, when we did 1,000 repetitions, there were some that were exactly the same, but they're usually a bit different. So now let's go back to the other screen and let's just take a peek at it and make sure that we fully understand it. Okay, so back to where we were, should say. There's 1,000 repetitions total. This right here, this is our that last rep. In other words, that last flip, the 1,000th flip. We'll see that the means, here we go, the narrow and the narrow, this was flipped, this first one, and these were all recorded, okay? So just like we did over here, you'll see the lines 5.2 to 5, around 5. So that's the matched pair there, the narrow being in red and the blue being the wide value. Remember how this is graphed is being determined by over here. This was then translated down to here, just like we did in the first case. And I just pointed with my finger, which is not helpful. So here the mean is 0.02. So that's actually pretty close to 0 in this case, right? Because it's definitely much closer to 0 than what we had when we actually did the study. So this is randomized, this is the study, and this is just one repetition. Then this number here, this mean of 0.02, goes right here, see, in this one? So there's that last repetition. So if you did it every time and watched for 1,000 reps, each one of these would get added in here. Each time you hit randomize, it would come in here somewhere, all right? So we look here, and when we come up with the null distribution, remember when we talked initially, or not that long ago, about our null hypothesis, the difference between narrow and wide long-term, so that population parameter, the difference we expected, if nothing special is happening, the null hypothesis, 0. And interestingly, it came out to be exactly 0 here. The standard deviation, this is for the null distribution, is 0.025. Now, when you do this on your own, is it going to come out slightly differently? Yes. Do I expect if I redid this myself right now, would it come out differently? Definitely. Okay, so this would come out as different number, it would come out with a different distribution. What I'm interested in now, and this is where you need to be careful with this, is I want to, am I looking at greater than or equal to, less than or equal to, or beyond? Remember, we're looking at different. So we want to look in both tails and see how many counts are as extreme or more extreme than 0.075. That was our study value, and I'm going to count. And I ended up with 0.002. That right here is my p-value, okay? There is my p-value. Now, if I did this again, would I come up with a slightly different p-value? Most likely yes, but would it be similar to what I got here? Also yes, okay? So you could have had in 0 out of 1,000. Now, remember when we do that, are we going to say that the p-value is 0? No, we're going to say it's less than 0.001. So we're saying it's very small. So there is our p-value, because remember we count how many and then divide by the total number of repetitions to give us the proportion, our p-value, the probability that we're way out here. So back to the notes. So we had already done this. We had gone to 1,000 repetitions and we clicked randomize and we talked through this. So we also came up with a p-value, and remember to count the samples. Sorry, apologize there. This is beyond, remember 0.075. In other words, different, how more extreme, how many are there that are more extreme than what we found in our study? So our p-value was calculated as 2 out of 1,000. Remember there was 2 that were at 0.075 or more extreme than, and that became 0.002. So let's interpret the p-value in the context of this study. We've done this lots of times, but remember, it's the same ideas. You just have to be very, very careful. We want to talk about the p-value here. We're not interpreting the whole study at this point. We're not drawing a conclusion. We're just talking about what the p-value tells us in the context of this study. So if on average, I went back to my hypotheses and used a lot of the same words, the narrow angle takes the same time as wide angle. So because remember, we always want to interpret the p-value in the context of the study, not just say the p-value is, because we've already done that. We've said the p-value is, and we see that it's a very small number. We would see 22 people take on average 0.075 seconds or even more. So more extreme, even further out, even bigger, with one strategy compared to the other, about 0.2% of the time. That's tiny, okay? That's very, very small. So now let's draw appropriate conclusions. And this should be 0.0. I did this, sorry, I did that with earlier and it came out with 0 instead of, so let's be consistent. Draw my conclusions. Remember, we want to look at SCG because the p-value is small, in this case 0.002, and the study was a randomized experiment. We can conclude that after accounting for runner skill, the strategy makes a difference in the runtime for players like those in the study. So generalizability, remember, we did not, this is just not a random sample. It was looking at runners, so there was a given sample. Causation, though, we can speak of because of there being, it was, they were randomly assigned, all right? So don't forget to look at SCG as you do that. To use theory-based inference, we can do that also. So that's using simulation, okay? Let's now go to, can we use theory-based? Because that's a lot of ways even easier. We can use normal approximation-based for paired data also, the approach to find a p-value and a confidence interval for paired data if it's valid if the number of pairs in the sample is at least 20, or it appears that the sample differences come from a normally distributed population. All right, so one of the two things can't be strongly skewed. All right, so we're going to now use the information that we have. You notice these are now numbered 1 sub I to be in relation to this I here. Is the normal approximation-based approach valid for finding a p-value and a confidence interval for the base running study data? Why or why not? What do you think? Would it be good? Well, we see the sample size. It's pretty close to 20. It's 22, which is greater than 20. If it was really skewed, we'd probably want bigger sample size. But when we actually look at the data, when we had it actually graphed, close your eyes if you get a little motion sick here. This is not really skewed. This is fairly evenly distributed. There's not a big skew. So there is, going back, and it's not too skewed. So yes, the normal approximation should be valid. So then I ask, regardless of whether you said it was good or not, we're going to use the theory-based inference applet to find and report the following. We're going to use that theory-based, it's the same applet we've been using along the way. So what you want to be really careful of, and I've made this mistake myself, make sure the hypotheses agree with those you stated. So I'm back at the applets page. So I'm going to close that down and, oh, bugger. I love when it tries to be helpful and locks me out. Okay, so go back to web applets. Theory-based under statistical inference here, we're going to do theory-based inference, which we've done quite a bit. Are we looking at proportions? No, we're looking at one mean. Remember, we're looking at just one mean, not two. We're not going to paste the data because we already have it. So I'm going to, I'd love you to do this on your own, but if not, well, actually just pause for a second and try it with the applet. See if you can come up with it. So what have I done so far? I've plugged in our sample size, 22, and I apologize that you can't see the mean X bar and the standard deviation of the sample S, but it's 0.075 for the mean and the sample standard deviation 0.088. So now what I want to do is the test of significance. Now this is where you want to be careful. It says my null hypothesis is equal 0. Think about what is our hypotheses for it in this case. Is it less than, greater than, or not equal to? This is where you want to make sure you have the right one, and I wanted not equal to. Now, one thing I want to point out is it didn't automatically calculate. Always remember then to hit calculate. Cool. Now, I have a standardized statistic, and I have a p-value, which is pretty neat. And you're like, yeah, Sonia, not neat. I know. Our standardized statistic is T because we're looking at means. T is 4. 4 is pretty big. Our p-value is very small. Not that much different than really what we calculated without, with just using simulation. So the other thing I would like is a confidence interval. The nice thing is now we can do that right here. Click confidence interval. This is where you can change the number for the confidence interval. You could have 95, you could have 90. So I'm going to make a note of these numbers and then go back to the notes. So I just wrote those down from the applet. Standardized statistic, T equals 4. My p-value is very small. It's 0.0007. And my 95% confidence interval is 0.036 to 0.014. Now this is where we have to be careful. We want to interpret the 95% confidence interval in the context of the study. First of all, before we do that, I just want to just observe that these numbers all agree. And you're like, well, how do you mean agree? They're very different. True. They are different, but our standardized statistic, we're saying we're 4 standard deviations away from the center. That's pretty far. And p-value being very small says, well, we're pretty far out there in the tail, so those both agree. How does that then relate to the confidence interval? Well, the confidence interval should not include 0, definitely, right? Because if it included 0, that would say that the null hypothesis is possible. Here, it does not include 0, right? We don't have 0 in there. We start at 0.036 and go to 0.114. So interpret the 95% confidence interval in the context of this study. So pause and give it a shot. So hopefully this is roughly where you came out to. We are 95% confident that such players will take somewhere between 0.036 to 0.014 seconds more on average when they use narrow arrow angle compared to the wide angle. Now, why do we have to say such players? Well, because these are professional or these are very serious athletes. It would be very different from like throwing me into the mix in terms of running. We do know we have a range, how much longer it will take. Can that make a difference? It's like, well, that's not many seconds. Well, in the game, it can make a big difference. I always wondered why they ran the angles they do, and well, now I see it. So from here, you're going to notice there is another example, age differences in couples. The solution is posted, but I would like you to work it on your own. Make sure you really have got this. And that takes care of day 25's lecture.